Assalamu alaikum wa rahmatullah. Welcome back to the new session of your lesson Oxidation and Reduction. At the end of the session you will be able to establish a qualitative electrochemical classification and predict whether an oxidation reduction reaction takes place or not by applying gamma rule. The materials you're going to need during this session are a pen, your chemistry book, and a worksheet that you are supplied with that includes the main ideas and applications related to the video. We have seen before that during a redox reaction, electrons move from one species to another. The species that loses electrons is said to be oxidized, while the species that gains the electrons is said to be reduced. The species that is oxidized or that undergoes oxidation is called the reducing agent, and the species that is reduced or undergoes reduction is called the oxidizing agent. A redox couple is presented by Mn plus M, and the half reaction of this couple is Mn plus N electrons gives M, or M gives Mn plus N electrons. An example of a redox reaction is Mg plus Cu2 plus gives Mg2 plus Cu. As you can see here, 2 electrons are transferred from Mg to Cu2 plus. Then we can say that Mg loses 2 electrons. When Mg loses these 2 electrons, it will form an Mg2 plus ion. Since Mg loses 2 electrons, then it undergoes oxidation, which is the electron loss. And since Cu2 plus gains the 2 electrons to form Cu, then we say that it undergoes reduction due to the gain of electrons, and we say that copper ion is reduced. Now, Mg undergoes oxidation, then we can say that it is the reducing agent. Cu2 plus undergoes reduction, then we can say that it is the oxidizing agent. Now, let's talk about the reaction between Cu2 plus Cu, between the two redox couples, Cu2 plus Cu and Ag plus Ag. Now, if we dip a copper strip in a silver nitrate solution, what happens? We can see that a white bright deposit is formed on the copper strip, while the solution, which was colorless, turns blue. This solution was colorless and now it turns blue. We can say that a redox reaction took place. Now, if we dip a silver strip in a copper sulfate solution, leave it for some time, look at the beaker and the strip again. Nothing happened neither to the silver strip nor to the copper sulfate solution. There are no changes. Then we can say that no redox reaction takes place between silver and Cu2 plus. Why is that? Here, when we dipped a copper strip in a silver nitrate solution where a redox reaction took place, we dipped a copper strip Cu in a silver nitrate solution, silver which contains silver ions, Ag plus. We can say that since a reaction took place, we can say that the copper metal Cu has reduced Ag plus. It caused the reduction of Ag plus. While when no redox reaction took place, when we dipped the silver strip in a copper sulfate solution, we can say that the silver metal did not reduce the copper ions Cu2 plus. Then we say that the reaction between the two redox couples Cu2 plus Cu and Ag plus Ag is spontaneous when the reagents are Cu and Ag plus. Means that when we dip a copper strip in a solution containing Ag plus ions, a reaction takes place, while when we dip a silver strip in a solution containing Cu2 plus ions, no reaction takes place. This reaction which occurs according to the equation Cu plus 2Ag plus gives Cu2 plus 2Ag. Which of these metals has a greater reducing power, has more reducing power? Is it copper or silver? In the previous slide we said that copper can reduce Ag+, while silver cannot reduce Cu2+. So we can deduce that the reducing power of copper is greater than the reducing power of silver. Now, this reducing power can be represented by an axis where we put the metals copper and silver and arrange them in there according to their increasing reducing power. It is very important to note that the increasing reducing power is downward. Now, we said that copper has a greater reducing power than silver. Then we put it down because the increasing reducing power is downward, and Ag, which has less reducing power than Cu, is put above it. This axis represents the reducing power of silver and copper. Also, in this case, Ag plus ion oxidizes copper metal, whereas Cu2 plus ion does not oxidize silver metal Ag. Which of these ions has more oxidizing power? Is it Ag plus or Cu2 plus? Of course, Ag plus can reduce Cu, then it has more oxidizing power, whereas Cu2 plus cannot oxidize Ag, then it has a less oxidizing power. The oxidizing power of Ag plus ion is greater than the oxidizing power of Cu2 plus ion. Again, these two ions can be arranged according to their oxidizing power on an axis which represents the increasing oxidizing power of the metal ion. In this axis, the increasing oxidizing power is upward. Now, since Ag plus has a greater oxidizing power than Cu2 plus ions, then it is put above Cu2 plus. And Cu2 plus has less oxidizing power, then it is put below Ag plus. This axis represents the oxidizing power of Cu2 plus and Ag plus ions. Now, we have two axes. The first one, which represents the increasing oxidizing power, and the second, which represents the increasing reducing power. Now, these two axes can be merged into one axis, which includes both increasing oxidizing power and increasing reducing power. As you can see here, the redox couple Ag plus Ag is set above Cu2 plus Cu. This forms the qualitative electrochemical classification of redox couples. Cu is below Ag in the increasing reducing power axis, so we can say that Cu is a stronger reducing agent than Ag, which is a weak reducing agent. And also in the increasing oxidizing power axis, we can say that Cu2 plus, which is below Ag plus, is a weak oxidizing agent, and Ag plus is a strong oxidizing agent. Look here, Ag plus is a strong oxidizing agent, while Ag is a weak reducing agent. Also, Cu2 plus is a weak oxidizing agent, while its metal is a strong oxidizing agent. So, this shows that the reducing power of metals varies inversely with the oxidizing power of their ions. Strong metal means weak ion. Strong ion means a weak metal. Then we can say that the greater the reducing power of metals, the lower the oxidizing power of their ions, and vice versa. For example, in the reaction between copper Cu and 2Ag plus silver ion, which gives CO2 plus 2Ag. Look at the axis. Cu is a strong reducing agent. We write a strong reducing agent. Ag plus is a strong oxidizing agent. Ag plus is a strong oxidizing agent. CO2 plus is a weak oxidizing agent, and Ag is a weak reducing agent. So the reaction is taking place between the strongest oxidizing agent, which is Ag plus, and the strongest reducing agent, which is Cu, to give CO2 plus and Ag. This is what we call the gamma rule. What does the gamma rule state? Gamma rule states that the reaction takes place between the strongest oxidizing agent and the strongest reducing agent to give a weak oxidizing agent and a weak reducing agent. As you can see here in the axis, it takes place between the oxidizing agent 1, which is the strongest oxidizing agent, and the strongest reducing agent to give the oxidizing agent 2, which is weak, and the weak reducing agent. The opposite of gamma rule does not proceed. A reaction cannot take place between the weak reducing agent and the weak oxidizing agent. Another example of a redox reaction is the reaction between the redox couple CO2 plus Cu and Fe2 plus Fe. Here we dip an iron bar in a copper sulfate solution. Leave for a few hours. We can see that there is a deposit of copper is formed on the iron bar, and the color of the solution fades. Look at the color of the solution, and compared to the initial color, we can see that the color of the solution fades. It means that there is a reaction that took place between Fe iron and CO2 plus ions in the solution. The reaction between the two redox couples, CO2 plus Cu and Fe2 plus Fe, is spontaneous when the reagents are Fe and CO2 plus. It's important to note that no reaction takes place between Fe2 plus and Cu. Now, in this case, we say that CO2 plus ions oxidize iron metal Fe. CO2 plus cause the oxidation of Fe, while Fe reduced the copper ions. It reduced them to Cu atoms, which we can see on the iron bar. Then CO2 plus, since it can oxidize iron metal, has a greater oxidizing power than Fe2 plus, and Fe, which reduces CO2 plus, has a greater reducing power than Cu. If we want to put them on an axis, look here, we said that CO2 plus has a greater oxidizing power than Fe2 plus. Then CO2 plus, we put it above Fe2 plus. And Fe, which has a greater reducing power than Cu, look here, the increasing reducing power is downward. Then we can say that Fe has a greater reducing power than Cu. The reducing power of metals and the oxidizing power of a metal are represented on an axis. The result of these two axes is called the electrochemical axis, which is shown here, which shows both the increasing oxidizing power of metals and the increasing reducing power of metals. The qualitative electrochemical classification allows to predict the spontaneity of oxidation reduction reaction between the two redox couples. The spontaneity of this oxidation reduction reactions to know that if it takes place spontaneously or not. Of course, to determine if a reaction takes place or not, we must apply the gamma. The summary of this lesson: first, the qualitative electrochemical classification arranges the oxidizing agents of Mn plus M couples according to an increasing order of oxidizing power, and reducing agents of these couples according to an increasing order of reducing power according to the axis. Also, the spontaneous reaction between two redox couples occurs between the stronger oxidizing agent and the stronger reducing agent according to the gamma rule. The reaction according to gamma rule takes place between the stronger oxidizing agent and the stronger reducing agent to give the weak oxidizing agent and the weak reducing agent. This session was prepared by teacher Antal Yassin, recorded by Mr. Mustafa Tlays, and supervised by teacher Hiba Badawi. Thanks for your listening.